Imagine looking up at the night sky, knowing that out there, billions of miles from Earth, a small world drifts in the cold and silent darkness, a world that, for decades, we thought we understood. Pluto, once the 9th planet in our solar system, now holds the title of dwarf planet, but that change in classification only deepened the mystery surrounding it. When the New Horizons spacecraft finally reached Pluto in 2015 after a journey of nearly a decade, it didn't just send back pictures, it sent back puzzles. The data revealed a landscape far more complex and dynamic than anyone had predicted: icy mountains, vast plains of frozen nitrogen, and even hints of a subsurface ocean. Suddenly, this distant, small world became a place of profound and unexpected wonder, challenging everything we thought we knew about the outer reaches of our cosmic neighborhood. What makes Pluto so endlessly fascinating isn't just its controversial status or its breathtaking beauty, it's the sheer number of unanswered questions it presents. Why does it have a beating heart of nitrogen ice that seems to reshape its surface? How can such a small, cold world possibly harbor geologic activity? And what secrets lie hidden beneath its frozen crust? Each discovery from New Horizons seemed to raise more questions than it answered, pulling us deeper into the intrigue of this enigmatic dwarf planet. It's almost as if Pluto is deliberately guarding its mysteries, inviting us, daring us, to look closer and unravel the truths hidden in its icy, distant realm. That's exactly what we're going to do together in this video. We're embarking on a journey to explore 25 of the most compelling unexplained mysteries of Pluto, from its bizarre atmosphere and puzzling geology to the possibility of hidden oceans and even the potential for life in the most unexpected places. This isn't just a story about a dwarf planet. It's a story about human curiosity, our drive to explore, and the awe-inspiring realization that even in the farthest, coldest corners of our solar system, wonder awaits. So settle in, open your mind to the possibilities, and get ready to see Pluto in a whole new light, as a world of mysteries waiting to be solved. And so our exploration begins with perhaps the most iconic and baffling feature discovered on this distant world: the immense, bright heart that dominates its surface. This is Tombaugh Regio, named in honor of Clyde Tombaugh, the astronomer who first discovered Pluto in 1930. From the moment New Horizons beamed back its first clear images, this heart-shaped region captured our collective imagination, but for scientists, it represented a profound and immediate mystery. Stretching over 1,000 miles across, it's not just a superficial marking. It's a massive geological feature that appears to be driving much of the activity on this tiny world. What makes this heart so puzzling is its stunning brightness and startlingly smooth texture, which stand in stark contrast to the darker, more heavily cratered terrain that surrounds it. This high albedo, or reflectivity, points to a surface composition that is very different from the rest of Pluto. Spectral analysis revealed that the heart is primarily made of nitrogen ice, with smaller amounts of methane and carbon monoxide ices. But the surrounding regions are cloaked in darker, reddish tholins, complex organic molecules created when methane is exposed to sunlight. This dramatic compositional difference begs the question: how did such a vast, uniform deposit of volatile ice form in this one specific location? And why has it remained so pristine and bright over billions of years? Initial theories about its origin immediately ran into challenges. One leading idea was that it could be an enormous impact basin, the result of a catastrophic collision with another object in the Kuiper belt. A giant impact could have resurfaced the area, perhaps even bringing up fresh ices from below, but the data from New Horizons complicated this story. The western half of the heart, an area called Sputnik Planitia, is incredibly smooth and shows no evidence of a crater rim. In fact, it's a deep basin that sits 3.5 kilometers below the surrounding terrain. If it was an impact, it was an event so powerful it fundamentally reshaped Pluto, but the lack of a classic crater structure leaves many scientists unsure. This leads to another compelling theory, cryovolcanism. Perhaps Pluto's internal heat, residual from its formation or generated by the decay of radioactive elements, is causing pockets of slushy, liquid nitrogen water to erupt onto the surface, constantly repaving this area and keeping it dazzlingly bright. This process could explain the lack of impact craters, suggesting the surface is geologically young and actively renewing itself. The very existence of such recent activity on a small, cold world that should have frozen solid eons ago is a mystery in itself, making the heart not just a feature to observe, but a dynamic, beating engine at the center of Pluto's greatest enigmas. This western lobe, Sputnik Planitia, is far more than just half of a recognizable shape. It is the most geologically youthful landscape ever observed in the outer solar system. Its surface is a vast, sprawling plain of frozen nitrogen, so remarkably smooth and unblemished that it looks as if it was poured onto Pluto's surface only yesterday in cosmic terms. The near-total absence of impact craters is what truly stuns planetary scientists. In a system as old as our own, every solid surface bears the scars of countless bombardments, a cosmic history book written in craters. For Sputnik Planitia to have so few means its surface cannot be more than a few million years old, a stunningly recent resurfacing event that defies all expectations for a small, icy body so far from the sun's warmth. The prevailing theory to explain this constant renewal points to a process of convection within the nitrogen ice itself. New Horizons images revealed a surface fractured into a stunning mosaic of polygonal cells, each spanning 20 to 30 miles across. These aren't static features, they are the visible tops of slow, churning currents, much like a lava lamp operating in ultra-slow motion. Heat from Pluto's interior rises up through the slab of nitrogen ice, causing warmer solid ice to buoyantly rise in the center of these cells, while the colder, denser ice at the edges sinks back down. This relentless, gentle churning continuously refreshes the surface, smoothing out any craters almost as soon as they form and presenting a forever youthful face to the cosmos. But this incredible process immediately raises a deeper, more fundamental question. What is the source of the internal heat required to power this activity? A body as small as Pluto should have lost its primordial heat billions of years ago, its interior frozen into a static, unchanging state. The existence of these convective cells is direct evidence that Pluto's interior is, against all odds, still warm and dynamic. This has led scientists to one of the most exciting and far-reaching hypotheses about this distant world, the possibility of a subsurface ocean of liquid water. The heat generated by the decay of radioactive elements in Pluto's rocky core, trapped and insulated by a thick shell of water ice, could be just enough to maintain a layer of liquid water beneath the surface. This internal warmth would not only prevent the nitrogen ice from freezing solid, but could also provide the thermal energy needed to drive the massive convection cells we see in Sputnik Planitia, making this bright heart not just a surface feature, but a window into a potentially habitable environment deep within. While the churning, youthful surface of Sputnik Planitia hints at dynamic forces within Pluto, the dwarf planet's activity doesn't stop at the ground. High above its icy plains lies an atmosphere that behaves in ways that are just as puzzling and dramatic. Unlike the stable, predictable air we have on Earth, Pluto's thin, hazy envelope is a world of extreme seasonal swings, expanding and contracting in a breathtaking cosmic dance as it travels along its highly elliptical 248-year orbit around the Sun. For decades, based on observations from Earth, scientists understood the basic rhythm. When Pluto is at its closest point to the Sun, ices on its surface heat up enough to sublimate, turning directly from a solid into a gas and causing the atmosphere to balloon outward. As it then journeys back into the deep freeze of the outer solar system, those gases are expected to refreeze and snow back down onto the surface, causing the atmosphere to all but vanish. This predictable cycle, however, was completely upended by the data from New Horizons. When the spacecraft performed its historic flyby in 2015, Pluto was on its way back out from its closest approach to the Sun, which it had reached 9 years earlier. According to all the models, its atmosphere should have already been in a period of rapid collapse, condensing and freezing back onto the surface as temperatures plummeted. But the measurements told a very different story. The atmospheric pressure at the surface was found to be only about 100,000th that of Earth's, which is incredibly thin, but it was still a factor of 10,000 higher than what many leading predictions had estimated for that point in Pluto's orbit. It was as if someone had left the gas on long after the stove was turned off. The atmosphere was stubbornly refusing to collapse as expected, presenting a major mystery that challenges our fundamental understanding of how small, icy worlds manage their volatile materials. So what is holding Pluto's atmosphere aloft against the pull of gravity and the cold of deep space? One compelling theory points back to that beating heart, Sputnik Planitia. This vast reservoir of volatile nitrogen ice may be acting as a massive thermal regulator for the entire world. Because of its high reflectivity and the latent heat involved in its phase changes, the ice sheet could be sublimating, turning from ice to gas at a much slower and more sustained rate than anticipated. It's possible that the convective churning we see on its surface is constantly bringing fresh, volatile ice up from below, providing a long-lasting fuel source for the atmosphere that delays its inevitable seasonal freeze-out. In this scenario, the heart isn't just a geological feature, it's the planetary scale engine that governs Pluto's climatic cycle. Another, even more intriguing possibility is that we are witnessing the delayed effects of Pluto's complex seasons. Its long orbit means a single season lasts for decades. The intense heating it received at its closest approach to the Sun may have created a kind of thermal inertia, where the subsurface layers of ice are still slowly releasing the stored heat from that period, continuing to sublimate ices and feed the atmosphere long after the external warmth has faded. This would be like a stone hearth remaining warm and radiating heat long after the fire has gone out. There's also the radical possibility of internal outgassing, that heat from Pluto's rocky core, perhaps from the decay of radioactive elements or even the gravitational tug of its large moon Charon, could be causing ices deep within the planet to sublimate. These gases would then find their way to the surface through cracks and fissures, providing a steady, non-seasonal trickle of material that supplements what is coming from the surface ices, creating an atmospheric budget far more complex than a simple sun-driven cycle. This ongoing enigma shows that Pluto's thin, hazy sky is not a passive shroud but an active, dynamic system, one that we are only beginning to comprehend. Leaving the smooth plains and hazy skies behind, we venture next to a landscape that looks less like part of a planet and more like a set from a surreal science fiction film. This is Tartarus Dorsa, a region near Pluto's equator dominated by a phenomenon known as the bladed terrain. Imagine a vast field of giant, jagged knives made of ice, some towering as high as skyscrapers and stretching for hundreds of miles across the frozen surface. The New Horizons images revealed this field of monumental ridges, all oriented in the same direction, creating a terrifying and beautiful vista that is utterly unique in our solar system. Nothing like this exists anywhere else we've explored, and its very presence on Pluto is a monumental puzzle for geologists. The composition of these blades is the first crucial clue. Spectral data confirmed they are primarily made of solid methane ice, not the nitrogen ice that dominates Sputnik Planitia. This distinction is vital because methane behaves very differently under Pluto's extreme conditions. The blades aren't the result of tectonic forces pushing mountains upward. Instead, they are thought to be a product of erosion. but an inversion of the process we're familiar with on Earth. Typically, erosion wears material down, carving out valleys and canyons. On Pluto, however, scientists believe a specific type of erosion may have actually sculpted these immense structures upward, leaving the hard ridges behind while the softer material around them was worn away over millions of years. The leading theory for their formation is a process called sublimation-driven erosion. On Pluto, the weak sunlight is still enough to cause solid methane ice to turn directly into gas. Over astronomical timescales, this isn't a uniform process. Perhaps the methane ice was originally deposited as a thick sheet across the region. As the sun's angle changed with Pluto's long seasons, it would have heated the ice preferentially on certain slopes. Those sun-facing slopes would sublimate faster, etching deep grooves and troughs into the ice sheet. The areas more shielded from the sun would sublimate much more slowly, leaving behind the sharp, towering spines we see today. It's a bit like an ice sculptor using sunlight as a chisel, but on a scale that is almost incomprehensibly vast and slow. This process, however, raises even more difficult questions. For such precise and gigantic features to form, the initial sheet of methane ice must have been incredibly pure and uniform. Any significant variation in composition or the presence of rocky debris would have disrupted the formation of these clean, oriented ridges. Furthermore, the blades are enormous, some reaching heights of several hundred meters. This suggests that the original ice deposit must have been astonishingly thick, perhaps a kilometer or more deep, to allow for this dramatic sculpting. Where did such a massive and pure reservoir of methane ice come from? Was it delivered by comets, or did it outgas from Pluto's interior in a single, massive event early in its history? The blades themselves are silent monuments to a past event we can only begin to guess at. Their orientation adds another layer to the mystery. The blades all align in the same general direction, which is a strong indicator that their formation is tied to Pluto's climate and its relationship with the Sun. Their alignment is likely a direct record of the prevailing direction of solar radiation and wind patterns over millions of years. By studying them, scientists aren't just looking at ice, they're reading a climatic history book written in ridges of methane. This makes Tartarus Dorsa an incredible natural laboratory for understanding long-term climate cycles on a world where a single season lasts for decades, offering clues about how Pluto's thin atmosphere and intense seasons can shape its geology in the most dramatic ways imaginable. Moving from the sun-etched blades of Tartarus Dorsa, our journey takes us to the very top and bottom of this small world, where we find another stark and colorful mystery painted across the landscape. Unlike the brilliant white of the heart or the steely blue of the methane ridges, Pluto's North Pole is stained a deep, rusty reddish brown. This isn't a trick of the light or a simple mineral deposit. It is a thick, complex coating of organic material known as tholins. These compounds are not native to Pluto in the traditional sense. They are literally created in the sky when the simple molecules in Pluto's thin atmosphere, methane and nitrogen, are bombarded by ultraviolet radiation from the distant sun. This cosmic chemistry experiment creates a haze of complex hydrocarbons that slowly snows down onto the surface, coloring everything it touches. Yet, the distribution of this material is anything but even, and its curious concentration at the poles presents a fascinating puzzle. The process of tholin formation is in itself a brilliant piece of cosmic alchemy. High above Pluto's surface, the weak but persistent UV radiation from the sun provides the energy needed to break apart the bonds in methane molecules. These fractured pieces are highly reactive radicals, which then eagerly collide and combine with other molecules, including nitrogen, to form entirely new, more complex compounds. These newly formed molecules begin to stick together, growing into tiny, reddish haze particles. Over vast stretches of time, these particles gradually drift down through the atmosphere, blanketing the landscape below in a fine, ruddy dust. This is the same process suspected to occur on other distant worlds like Saturn's moon Titan, giving them their distinctive orange hue. On Pluto, however, this process seems to have a very specific and curious destination. The central mystery is not that tholins exist, but why they have accumulated so heavily and specifically at the polar regions. If they are formed high in the atmosphere and fall uniformly, we might expect to find a more even, global distribution of this reddish gunk. Instead, the poles are significantly darker and redder than the mid-latitudes and the equator. This suggests that powerful and specific forces are at work, actively concentrating this organic snow in these particular areas. One of the most compelling explanations involves Pluto's extreme axial tilt and its incredibly long seasons. Much like Uranus, Pluto is essentially tipped over on its side, with its poles pointing toward the Sun for extended periods during its orbit. For decades at a time, one pole is in constant sunlight while the other is plunged into continuous darkness. This radical seasonal cycle could be creating a unique cold trap at the pole experiencing its long, dark winter. During this period, temperatures at the winter pole plummet to their absolute lowest, becoming the coldest place on the entire world. Scientists theorize that the atmosphere itself may actually freeze and collapse onto the surface at the pole. As the atmospheric gases condense, they could effectively scrub the tholin haze particles out of the sky, depositing them in a concentrated layer at the pole. Then, when the seasons eventually change and the sun rises on that pole, the highly volatile nitrogen and methane ices would sublimate back into the atmosphere, but the less volatile, more resilient tholins would be left behind as a permanent stain. This process, repeated over millions of years, would leave an ever-thickening layer of organic gunk at each pole, a lasting record of countless seasonal cycles. There is also the intriguing possibility of atmospheric circulation playing a key role. The dramatic temperature differences between the sunlit and dark halves of Pluto could drive powerful winds that transport the haze particles toward the poles. The poles may act as a kind of chemical sink, where atmospheric patterns conspire to dump their complex organic cargo. Each new layer of tholins deposited on the surface is then subjected to further processing by solar radiation, potentially creating even more complex molecules. This means the reddish caps we see are not a static deposit. They are likely a dynamic, evolving chemical library, with new compounds being created both in the sky and right on the icy surface. The specific chemical pathways involved, exactly which molecules form, and in what order remain a subject of intense speculation and modeling, as these are processes incredibly difficult to replicate in Earth laboratories. The presence of such a vast reservoir of complex organics is profoundly significant, and not just for understanding Pluto's weather patterns. Tholins are rich in carbon, nitrogen, and hydrogen, the very building blocks of life as we know it. While they are not themselves alive, they represent the prebiotic starting materials that, under the right conditions, could lead to the formation of amino acids and nucleotides. This raises a captivating, if speculative, question. If Pluto does indeed harbor a subsurface liquid water ocean, as some evidence suggests, could these complex organic molecules from the poles ever find a way to interact with that liquid water? While the surface is far too cold for life, the delivery of these prebiotic compounds through geologic processes into a warmer, watery environment below could set the stage for chemistry of astounding complexity. The red polar caps, therefore, are more than just a curious stain. They are a testament to the universe's innate ability to create complexity from simplicity, and they mark Pluto as a world rich in the very ingredients that are fundamental to biology. But perhaps the strangest and most whimsical sight in all of Sputnik Planitia is the one that seems to defy the very laws of physics as we know them, the floating hills. Scattered across the vast, convecting nitrogen plain are countless isolated hills, some several miles across and hundreds of feet high. Their composition alone makes them alien in this environment. spectral analysis confirms they are made of solid water ice, which is fundamentally different from the softer nitrogen ice that surrounds them. Water ice on Pluto is about as hard as bedrock is on Earth, while the nitrogen ice is more like a malleable, flowing glacier. This stark difference in material is just the beginning of the mystery, because these aren't just hills sitting on the surface. They are islands truly adrift and moving slowly across a frozen sea. The principle that allows this bizarre phenomenon is simple yet stunning: density. A solid object will float on a fluid if it is less dense than that fluid. We see this every day with an ice cube floating in a glass of water. On Pluto, the roles are spectacularly reversed. The hills of water ice are actually less dense than the solid nitrogen ice that makes up the plains of Sputnik Planitia. This means the massive nitrogen glacier, though it appears solid, is behaving like a viscous fluid over geological timescales. The water ice hills are buoyant, and as the nitrogen ice slowly churns and convects beneath them, these hills are carried along like icebergs drifting in a sluggish, frozen Arctic current. They are literally floating on a sea of solid nitrogen. Their movement, however, is not random. As new horizons mapped their distribution, a fascinating pattern emerged. These hills don't appear in a chaotic scatter. Instead, they are often organized into long, graceful chains or clustered into groups, almost as if they were marching in formation across the plain. This organization is the central puzzle. If they were simply random chunks of Pluto's ancient, rugged water ice crust that broke off and became stranded, we would expect to see a more disordered, haphazard arrangement. Their alignment into chains and clusters suggests they are being influenced and guided by a larger, unseen force. The most likely explanation points directly to the massive convection cells operating beneath the surface. The slow, cyclical movement of this nitrogen ice is not uniform. It flows in specific directions along the boundaries between cells. Scientists believe these floating hills are congregating in the spots where multiple convection cells meet. At these convergence zones, the flow patterns might push the hills together, herding them into groups. Alternatively, the hills could be tracing the paths of the flowing nitrogen, getting caught in its currents and strung out into long lines that map the invisible flow of the glacier below, much like leaves gathering in the eddies of a stream or foam collecting along oceanic convergence zones on Earth. This still leaves the profound question of their origin. Where did these immense chunks of water ice come from in the first place? One compelling theory suggests they are fragments from the rugged highlands that border Sputnik Planitia, perhaps pieces that broke off and tumbled into the basin long ago. Another, more dramatic idea is that they are the tips of submerged mountains, the highest peaks of the actual basement rock underlying the nitrogen ice, which is so deeply buried that only these summits protrude above the frozen plain. A third possibility is that they are the icy equivalent of terrestrial icebergs, calved from the shores of the water ice highlands that surround this vast basin. Regardless of their source, their current journey is a slow-motion ballet, choreographed by the hidden currents of a convecting glacier on a world billions of miles from the sun, presenting a serene and beautiful mystery that challenges our understanding of geology itself. And just when we thought Pluto's geological surprises couldn't get any more extreme, we encounter a mountain that defies simple explanation. A structure so immense it rivals the largest volcanoes on Earth, yet may be powered by something far more exotic than molten rock. This is Right Mons, a towering feature that rises nearly 2.5 miles above its surroundings and stretches over 90 miles across at its base, making it comparable in size to Hawaii's Mauna Loa. But unlike its terrestrial counterparts, Right Mons isn't belching fire and lava. If the prevailing theories are correct, it could be a cryovolcano, an ice volcano that once erupted a frigid, slushy mixture of water ice, ammonia, nitrogen, or methane. The very existence of such a massive cryovolcanic construct on a small, cold world is a staggering concept, yet the most compelling mysteries are written in the dark, haunting streaks that stain its slopes. The most striking feature of Right Mons is not its height, but its profound central depression, a gaping hole in its summit that is over 40 miles wide and plunges deep into the mountain's heart. This colossal pit is a key piece of evidence supporting the cryovolcano hypothesis. On Earth, a large caldera typically forms when a volcano collapses into its own emptied magma chamber after a massive eruption. By analogy, the vast depression at the top of Right Mons could be the scar left behind after a tremendous eruption of cryomagma drained a subsurface reservoir, causing the entire structure to slump inward. The mountain's gentle, sloping sides further suggest it was built up layer by layer over eons by repeated eruptions, each one coating the landscape in a new layer of frozen slush. But the truly enigmatic feature, the one that sets this mountain apart and fuels intense debate, is the dark, reddish material that appears to streak down its flanks. In the high-resolution images from New Horizons, these streaks stand out in stark contrast to the brighter, water ice-rich material that makes up the bulk of the mountain. They look for all the world like stains, as if some dark liquid or sludge has oozed from the summit caldera or from fissures on the slopes and trickled downward, freezing in place and leaving a permanent record of its passage. This material doesn't match the composition of the surrounding plains. Its spectral signature points to something far more complex and potentially organic in nature. So what is this mysterious dark residue? One compelling possibility is that it is a form of cryolava, but not the relatively clean water ice slush we might expect. Instead, it could be a complex cocktail of material erupted from deep within Pluto. If Right Mons is indeed a cryovolcano, its plumbing would tap into the dwarf planet's interior, potentially reaching a layer that is rich in ammonia hydrates, salts, and complex organic compounds like the tholins we see coloring the poles. An eruption could bring this dark, viscous mixture to the surface, where it would flow for a time before freezing solid on the cold slopes, leaving behind the dark streaks we see today. In this scenario, the streaks are a literal sample of Pluto's deep interior, a frozen snapshot of its inner chemistry splashed across the landscape. Another, even more intriguing idea is that the dark streaks are not the product of a single violent eruption, but evidence of a slower, more persistent process. They could be the residue from repeated episodes of gentle seepage or sweating, where volatile compounds and organic-rich ices slowly sublime away from the surface, leaving behind a concentrated lag deposit of darker, less volatile material. Over millions of years, this process could create the appearance of flows, tracing the paths where material most efficiently escaped from the mountain's interior. This would make Right Mons not a violently explosive volcano, but a weepy, oozing mountain, slowly exhaling its secrets over geological time. The presence of such organics is what elevates this mystery from a geological curiosity to a subject of profound astrobiological interest. If the dark streaks are indeed composed of complex carbon-rich molecules, their eruption from the interior suggests that Pluto's subsurface environment is not just warm but chemically active. The same internal heat that might maintain a subsurface ocean could also be driving chemical reactions between water, rock, and simple organic compounds, creating ever more complex molecules. Right Mons could therefore be a rare window, offering us a glimpse of the complex chemistry that might be occurring in the dark, warm depths beneath Pluto's icy shell, a chemistry that could be the first step on the long road toward the building blocks of life. But the most dramatic illustration of Pluto's variable face is found in its most famous duo of features, locked in a perpetual celestial dance of light and dark. On one side lies the brilliant, almost blindingly white expanse of Sputnik Planitia, the western lobe of the heart. Its surface, made of fresh nitrogen ice, reflects a tremendous amount of sunlight, giving it an albedo comparable to fresh snow. But right next to it, abutting its eastern edge, sprawls the sprawling, dark blemish of Cthulhu Macula. This vast region, larger than the state of Alaska, is one of the darkest landscapes in the entire solar system, with an albedo barely higher than charcoal. The border between them is not a gradual blending of tones, it is a razor-sharp line, a stark and sudden cliff where brilliant white instantly gives way to profound darkness, as if drawn by a cosmic artist with a perfectly steady hand. The composition of these two regions explains their appearance but deepens the mystery of their coexistence. Sputnik's high reflectivity comes from its vast deposits of nitrogen, methane, and carbon monoxide ices, which are highly volatile and excellent at scattering light. Cthulhu Macula, by contrast, is an ancient, heavily cratered terrain primarily composed of water ice, which is as hard as rock at Pluto's temperatures. But it's not the water ice itself that is dark. It is the thick layer of complex, reddish-brown organic gunk known as tholins that coats its surface. These tholins are created over eons when methane in Pluto's thin atmosphere is broken apart by ultraviolet light from the sun, forming complex hydrocarbons that eventually snow down to the surface. So we have one area that is actively replenishing its bright, volatile ice, and another that is passively collecting a dark, organic sludge. This presents the central puzzle. Why does this thick, dark coating of tholins accumulate so heavily on Cthulhu Macula, but not on Sputnik Planitia, especially when they are immediate neighbors? If the tholin snow falls globally, why hasn't it turned the entire planet a uniform reddish-gray? The answer seems to lie in the dramatic differences in geological activity between the two regions. Sputnik Planitia is a dynamic, constantly churning engine. Its convective cells are continuously refreshing its surface, bringing up new, pristine ice from below. Any dark tholin particles that settle on its surface are quickly buried or drawn down into the interior by this relentless geological turnover, preventing them from building up and maintaining the region's brilliant whiteness. Cthulhu Macula, on the other hand, is a geological relic. Its heavily cratered surface indicates it is incredibly ancient, perhaps dating back billions of years to the late heavy bombardment period. This is a landscape that has been geologically dead for eons, with no internal activity to refresh or cleanse its surface. Any tholins that have settled here over millions of years have simply accumulated into a thicker and thicker layer, creating a permanent dark stain. It acts as a cosmic trap for this organic dust, a static canvas upon which the slow rain of hydrocarbons paints an ever darker picture. Yet this explanation still feels incomplete. Why is the boundary between them so incredibly sharp? A gradual mixing at the edges might be expected, but the transition is abrupt. This suggests a powerful and ongoing process is actively maintaining this stark division. One theory points to atmospheric feedback loops. The bright surface of Sputnik Planitia reflects sunlight, helping to keep it cold and stable. The dark surface of Cthulhu Macula, however, absorbs solar energy, making it slightly warmer. This temperature difference could create a very localized atmospheric circulation pattern, where gases sublimating from the warmer dark region flow toward and refreeze onto the colder bright region, effectively creating a natural barrier that prevents the dark tholins from drifting across the border. The two regions may be locked in a self-sustaining cycle, each one reinforcing the other's identity through their interaction with Pluto's faint sunlight and wispy atmosphere, creating a planetary scale yin and yang that has persisted for millennia. Before New Horizons, our understanding of Pluto's surface chemistry was, in hindsight, almost charmingly simplistic. Based on Earth-based telescopic observations and theoretical models, many scientists anticipated finding a relatively uniform, global layer of methane frost blanketing the dwarf planet. The logic was sound, with surface temperatures hovering around -380 degrees Fahrenheit. Methane, a volatile compound, should freeze out of the atmosphere and coat the entire landscape in a fine, even frost, much like a deep freezer developing a layer of ice. When the first stunning images from the spacecraft arrived, they revealed a world of stunning geological diversity. but one thing was conspicuously absent that predicted global frosting of methane. Instead, the distribution of this simple hydrocarbon was maddeningly complex and patchy, concentrated in specific high-altitude regions and almost entirely missing from the vast, low-lying plains. This unexpected patchiness forced a complete rethink of the processes governing Pluto's surface-atmosphere interactions, revealing a far more dynamic and selective world than anyone had imagined. The mystery deepens when we look at exactly where the methane prefers to accumulate. It isn't scattered randomly, it has a pronounced preference for high ground. The bright, lofty mountain peaks, particularly those surrounding Sputnik Planitia and within the rugged terrain of Viking Terror, are often covered in a bright coating of methane ice, gleaming brilliantly in the weak sunlight. In stark contrast, the vast, smooth plains of Sputnik Planitia itself, a basin sitting kilometers lower than the surrounding highlands, are almost completely devoid of methane frost. This altitudinal segregation is a massive clue, pointing directly to the role of temperature and Pluto's complex climate cycles. The key lies in a process known as the cold trap effect. On a world with an atmosphere, even one as thin as Pluto's, gases will naturally circulate. The low-lying basins like Sputnik Planitia are not only topographical depressions but also thermal ones. They become the coldest places on the planet as cold air, being denser, sinks and pools there. This creates a fascinating atmospheric sorting mechanism. The nitrogen ice that dominates Sputnik Planitia maintains an incredibly cold and stable surface temperature, one that is actually too cold for methane to exist as a frost permanently. Any methane gas in the atmosphere that drifts over this frigid basin will find it energetically unfavorable to freeze out. It remains a gas. Meanwhile, the sunnier, higher altitude regions, while still profoundly cold, are just that tiny bit warmer relative to the profound chill of the basins. This slight thermal difference is enough to make it favorable for methane to deposit directly from the atmosphere onto these mountain peaks as a bright, reflective frost. It's a process of fractional distillation on a planetary scale, where Pluto's topography and extreme temperature gradients act like a giant chemical refinery, meticulously separating different ices based on their unique freezing points. The story, however, is not solely one of atmospheric condensation. The type of ice already present on the surface plays a critical role in determining whether methane can stick around. This is where the concept of competition between volatiles comes into play. Sputnik Planitia is dominated by a thick slab of nitrogen ice, which is highly volatile and constantly turning over through convection. A methane molecule landing on this active, churning surface doesn't stand a chance. It's either quickly buried by the convecting nitrogen, destroyed by solar radiation, or simply fails to bond effectively with the nitrogen substrate, eventually sublimating back into the atmosphere. The water ice that forms Pluto's rugged bedrock mountains, on the other hand, provides a much more stable and welcoming landing pad. Water ice is far less volatile at Pluto's temperatures, creating a static, long-lasting surface. When methane gas freezes onto this water ice bedrock, it can form a stable, coherent layer that persists for long periods, building up into the bright caps we see on the highest peaks. The methane isn't just falling out of the sky, it's choosing its real estate carefully, seeking out the most stable and favorable neighborhoods on an otherwise dynamic and unforgiving world. This brings us to one of the most profound and far-reaching mysteries of all, the possibility that Pluto, a world so distant and cold, might be hiding a vast, liquid water ocean deep beneath its icy surface. The evidence for this is not something we can see directly, but it is written into the very orientation and structure of the dwarf planet itself, and it centers on that massive, heart-shaped feature, Sputnik Planitia. You see, Pluto and its largest moon, Charon, are locked in a unique gravitational embrace called a tidal lock. This means they always show the same face to each other as they orbit their common center of gravity. What's absolutely fascinating is that Sputnik Planitia is located almost perfectly on the tidal axis, the imaginary line connecting Pluto's center to Charon's. It sits directly opposite its massive moon, a positioning that is astronomically too precise to be a mere coincidence. This perfect alignment points to a phenomenon known as true polar wander. The basic idea is that any spinning object, whether a top or a planet, will naturally seek the most stable rotation possible. For a world like Pluto, the most stable state is to have its mass distributed evenly along its equator. A significant extra weight anywhere else would cause the entire planet to literally reorient itself over millions of years, until that heavy spot was pushed toward the equator. Sputnik Planitia is that heavy spot. The nitrogen ice filling that enormous basin represents a colossal positive mass anomaly, a huge concentration of weight. But here's the incredible part. The basin itself is a negative mass anomaly. It's a giant hole. For the entire feature to act as a massive weight, something incredibly dense must be hiding underneath it, providing the gravitational tug to make that entire region much heavier than the rest of Pluto. That something is the leading candidate for a subsurface ocean. Scientists hypothesize that when a massive object struck Pluto billions of years ago, it carved out the Sputnik Planitia basin. If a global ocean of liquid water existed beneath the ice shell at that time, the impact would have thinned the crust dramatically at the point of impact. Because water is denser than ice, the liquid ocean beneath would have welled up into this newly thinned area, creating a huge bulge of dense material that effectively plugged the hole with a massive gravitational anchor. This dense plug is what then caused the entire planet to slowly roll over, like a weighted ball finding its balance point, until Sputnik Planitia settled directly on the tidal axis facing Charon, forever locking this heavy feature into its current stable position. The very existence of a liquid ocean today, however, is a monumental thermal puzzle. A body as small as Pluto should have lost the heat from its formation billions of years ago, its interior frozen solid into a static, unchanging state. For an ocean to remain liquid, a potent and persistent heat source is required. The decay of radioactive elements like potassium, uranium, and thorium within Pluto's rocky core is the most likely candidate, but models show this might not be enough on its own to prevent a global freeze. This has led to other intriguing possibilities, such as the heat generated by the crystallization of the ocean itself. As the ocean slowly freezes from the bottom up, the act of water turning to ice actually releases latent heat, which could help keep the remaining water above it in a liquid state for billions of years longer than previously thought. Another captivating theory involves antifreeze. The composition of this hidden sea is almost certainly not pure water. Data from New Horizons suggests the presence of ammonia hydrates on Pluto's surface, which could be a telltale sign of what's happening below. Ammonia is a powerful antifreeze, and even a relatively small amount mixed into the water could drastically lower its freezing point, allowing it to remain liquid at the frigid temperatures and immense pressures found deep within Pluto's interior. This wouldn't be a warm, tropical sea. It would be a cold, dense, slushy brine, perhaps more akin to a liquid muddle of water, ammonia, and various salts, but liquid nonetheless. The potential implications of this are staggering. If a liquid water ocean exists on Pluto, it fundamentally reshapes our understanding of where life could potentially arise in our solar system. We once thought habitable zones were limited to the region around a star where temperatures could support liquid water on the surface. But Pluto demonstrates that tidal forces and internal radioactivity can maintain liquid water oceans far outside this traditional zone, deep within icy worlds. This opens up a vast new array of possibilities, not just on Pluto, but on other Kuiper belt objects and moons throughout the outer solar system, suggesting that life, in its most basic forms, might be a far more common phenomenon in the cold, dark reaches of space than we ever dared to imagine. This brings us to a discovery so counterintuitive it seemed to defy the basic laws of physics: vast fields of dunes on Pluto's surface. When the New Horizons team first spotted these features in the high-resolution images of Sputnik Planitia's western border, near the Al Idrisi Montes mountain range, the initial reaction was one of pure disbelief. Dunes, by their very definition, are wind-sculpted landforms requiring an atmosphere with enough substance to lift and carry tiny grains of sand or dust across great distances. Yet, everything we thought we knew about Pluto argued this was impossible. Its atmospheric pressure is a mere 100,000th of Earth's, a near vacuum so thin that a human visitor would experience it more as the void of space than as a true sky. The very idea that this wispy envelope could muster winds powerful enough to move solid particles and pile them into organized structures was on its face utterly absurd. And yet, there they were, sprawling, organized ridges that bore the unmistakable signature of aeolian or wind-driven processes. The first and most pressing mystery was identifying the very substance of these dunes. What material could possibly be light enough and small enough for Pluto's phantom thin winds to pick up and carry? The answer, revealed through meticulous spectral analysis, was as unexpected as the dunes themselves: solid granules of methane ice. This wasn't sand as we know it on Earth, but tiny, sand-sized pellets of frozen methane. The source of this material appears to be the nearby mountains, which are composed primarily of water ice but are coated in a bright frost of methane. The process likely begins when weak sunlight causes patches of this methane frost to sublimate directly from solid to gas, launching tiny neighboring ice crystals into the air in the process. Alternatively, seasonal temperature changes could cause the brittle methane ice to fracture into tiny, granular particles, creating a vast supply of dune-building material ready to be moved. But this only solved half the puzzle. The far greater challenge was explaining the how, generating the wind force needed for saltation, the bouncing, hopping motion of grains that builds dunes in an atmosphere as thin as Pluto's requires extraordinary conditions. The key, scientists believe, lies in a remarkable and previously unforeseen atmospheric phenomenon. While Pluto's average atmospheric pressure is incredibly low, it doesn't mean the air is completely still. The driving force is likely the drastic difference in temperature across the dwarf planet's surface. The bright, nitrogen ice plains of Sputnik Planitia remain at a near constant and incredibly cold temperature. But the darker, water ice mountain ranges that border them absorb more of the sun's feeble energy, warming up slightly. This temperature contrast, however minor, can create pressure gradients. As the darker slopes heat up, they cause the thin layer of air above them to expand and rise, creating a localized area of slightly lower pressure. To equalize this, cooler, denser air from the frigid plains then rushes downslope, flowing from the high-pressure zone over the ice fields toward the low-pressure zone over the mountains. On Earth, this same process creates katabatic winds, like the powerful gusts that flow off glaciers and ice sheets. On Pluto, the physics are the same, but the environment is alien. The gentle breezes generated by this process are estimated to move at a relatively sedate pace, perhaps only a few miles per hour. But in an environment of such incredibly low gravity and minimal atmospheric density, even the softest whisper of a wind can achieve what a hurricane would on Earth. The minimal force required to lift a tiny methane grain in Pluto's weak gravity is so small that these gentle, diurnal winds are more than sufficient to get the job done, initiating a slow, majestic dance of ice particles across the landscape. The final piece of the mystery is the dune's stunning organization and preservation. They appear as long, linear ridges, often arranged in vast, orderly patterns. This level of organization implies that the winds are not random gusts, but are remarkably consistent in their direction and strength over vast stretches of geological time. They are a permanent feature of Pluto's climate, dictated by the unchanging topography of the mountain ranges and the ice plains. Furthermore, the extreme cold ensures that once a dune forms, it is essentially frozen in time. There is no liquid water or significant geological activity to erode them away. These are not transient features shaped by a passing storm. They are permanent monuments to the gentle, persistent caress of a barely their wind, a testament to the fact that even in the most tenuous of environments, the universe finds a way to create breathtaking and familiar complexity. This incredible contrast between ancient and modern isn't just a curiosity, it's one of the most fundamental mysteries of Pluto's very existence. On one side of this world, we have the sprawling darkness of Kuiper Macula, a terrain so heavily cratered it serves as a cosmic history book, its surface pockmarked with the scars of impacts that likely occurred billions of years ago. This is a landscape that has been geologically dead for eons, a silent testament to a violent early solar system. Yet, just next door, the brilliant white plains of Sputnik Planitia present a surface that is almost unnervingly smooth, with a near-total absence of impact craters that indicates it cannot be more than a few million years old. To find such a stark disparity in geological age right next to each other is like discovering a pristine, freshly paved highway running directly through the ruins of an ancient Roman city. It completely upends our understanding of how small, icy worlds evolve and demands an explanation for the powerful forces that are still actively repaving parts of this distant world. The sheer youth of Sputnik Planitia is the real head-scratcher here. In a system as old as ours, every solid surface should be saturated with craters. The fact that this vast plain is so smooth means something is actively erasing those scars, and it's doing so on a timescale that is, astronomically speaking, the blink of an eye. The convection we see in the nitrogen ice is the immediate mechanism, that slow churning that constantly refreshes the surface, but that process itself requires a powerful and persistent engine beneath it. This is the core of the mystery. What energy source could possibly be driving this profound geological activity on a small, cold body that should have frozen solid billions of years ago? A world like Pluto lacks the massive gravitational tug from a giant planet that drives the spectacular geology on moons like Enceladus or Io. So it must have an internal power source, and the most compelling candidate is the slow and steady decay of radioactive elements like potassium, uranium, and thorium locked within its rocky core. But there's a problem with that seemingly straightforward answer. For a body Pluto's size, the heat produced by radiogenic decay alone is generally thought to be insufficient to maintain the level of activity we're witnessing for billions of years. The heat should have dissipated long ago. This forces us to consider more exotic and fascinating possibilities. One is the idea of a subsurface ocean acting as a global thermal battery. If a layer of liquid water exists between the ice shell and the rocky core, it could efficiently transfer heat from the core upwards, preventing it from being trapped and helping to drive the convection we see at the surface. The initial heat from Pluto's formation, combined with the heat released as this ocean very slowly freezes, could provide a long-lasting thermal boost that stretches the planet's geological lifespan far beyond our previous estimates. Another captivating theory involves the unique properties of the ices themselves. The nitrogen ice that fills Sputnik Planitia is an incredibly efficient insulator. This thick blanket could be trapping what little internal heat Pluto has left, creating a kind of planetary thermos effect that maintains the warmth needed for sluggish convection to continue. It's also possible that the very act of convection itself generates additional heat through friction, as the massive blocks of ice slowly grind against each other in their cyclical dance. This would create a self-sustaining feedback loop where the movement generates the heat needed to perpetuate the movement. The presence of potential antifreezes like ammonia mixed into the subsurface ocean could further complicate the thermal picture, lowering the freezing point and allowing geological activity to persist at much colder temperatures than we'd ever think possible. Ultimately, the stark age disparity on Pluto's surface is a direct challenge to our models of planetary thermodynamics, forcing us to reconsider just how long small worlds can remain vibrant, active, and full of surprises. Scattered across Pluto's dark, ancient highlands are craters that seem to be wearing brilliant white crowns. These are the enigmatic halo craters, and one of the most striking examples is Elliott crater. From above, it looks as if someone dropped a stone into a pond of black ink, creating a perfect splash of bright material that forms a stunning, luminous ring around the entire impact site. This isn't a trick of the light or a simple trickle of ejecta. It's a near-perfect, symmetrical halo that stands in stark, brilliant contrast to the dark, Tholen-stained terrain it sits upon. The immediate and obvious question is what this dazzling material could possibly be, and why it has been laid down in such a precisely defined ring instead of being scattered randomly by the violence of the impact. The leading hypothesis points to the most straightforward explanation. These bright halos are essentially the planet's fresh skin exposed by a cosmic wound. Pluto's global bedrock is water ice, which is brilliantly white, but this bedrock is almost everywhere blanketed by a deep layer of dark, reddish tholins, those complex organic polymers that snow down from the atmosphere over eons. When an asteroid or comet slams into the surface, the tremendous force of the impact blasts away this dark surface layer, excavating material from below and scattering it around the crater. In this scenario, the bright halo is simply a blanket of pristine water ice ejecta, excavated from the subsurface and thrown outward, creating a brilliant ring of fresh, unspoiled material that hasn't yet been darkened by the continual fallout of atmospheric tholins. This simple excavation theory, however, runs into a significant complication when we look at the specific layout of these halos. In many cases, the bright material isn't distributed evenly in all directions, as one would expect from a typical explosion. Instead, it often forms a very distinct and narrow ring that seems to outline the crater's rim almost perfectly. This suggests the impactor may have struck at a very shallow angle, perhaps skimming across the surface and scooping up a specific layer of material to create that precise ring-like deposit. Alternatively, the impact could have been so forceful that it melted the subsurface water ice, creating a slurry of flash-melted ice and slush that was splashed outward in a more liquid-like state before instantly refreezing into a solid, gleaming ring. This would account for the halo's defined and almost fluid appearance, but there's another, even more intriguing possibility, that the bright material isn't just plain water ice at all. Spectral data from New Horizons offers a crucial clue. The composition of these halos shows a spectral signature that is consistent with water ice, but it also suggests the ice here is in an unusually pure and crystalline state. This has led some scientists to propose that the impact event itself might have fundamentally altered the ice at the crater's rim. The instantaneous and immense pressure and heat generated by the impact could have annealed the ice, changing its structure and making it more reflective. It's like the cosmic impact delivered a powerful blast of energy that effectively polished the ice, leaving behind a permanently brighter and more reflective ring that withstands the darkening effects of tholin accumulation far longer than the surrounding terrain. The longevity of these bright halos presents its own fascinating puzzle. If tholins are constantly snowing down from the atmosphere, why haven't these brilliant rings been dimmed and reddened over time? Their persistence suggests they are either very young or that something is actively keeping them clean. Perhaps the ice in the halo is so pure and dense that tholins have a difficult time adhering to its surface, causing the dark material to simply blow away in Pluto's faint winds before it can build up. Or maybe the geometry of the crater rim itself creates unique microclimates, perhaps slightly different temperature or wind patterns, that prevent the tholins from accumulating there as efficiently as they do on the flatter plains. Each halo crater, therefore, is not just a remnant of a single violent event, but an ongoing experiment in surface processes, a dynamic interplay between deposition and erosion that has been running for millions of years on a frozen world at the edge of our solar system. Yet, to truly grasp the scale and intricacy of this phenomenon, we must descend from the orbital view and examine the breathtaking details captured by New Horizons. The surface of Sputnik Planitia is not a flat, featureless sheet of white. It is a stunningly complex mosaic fractured into a series of polygonal cells, each spanning an impressive 20 to 30 miles across. The boundaries between these cells are marked by subtle, dark lines, creating a pattern that looks almost like a cracked desert floor or the skin of a dried-up lake bed, but on a planetary scale. These are not static cracks, they are the visible surface expression of a massive, slow-motion churning happening deep within the nitrogen ice. This is the clearest evidence of convection we have ever seen on another world, a process where heat from below causes warmer material to rise, cool at the surface, and then sink back down again, creating a continuous cyclical motion. The mechanics of this process in nitrogen ice are as exotic as Pluto itself. Unlike water ice, which is hard and rigid at these temperatures, solid nitrogen is a remarkably malleable material. Under the immense pressure of its own overlying layers and the gentle warmth from Pluto's interior, this nitrogen ice behaves less like a solid block and more like an incredibly viscous fluid, something akin to thick honey or a glacier flowing in ultra-slow motion. The heat, however minimal, provides just enough energy to make the ice slightly less dense in certain spots. These warmed patches then become buoyant, slowly rising towards the surface over thousands of years. Once they reach the top, they radiate their minuscule heat into the void of space, cool down, become denser, and then begin their slow descent back into the depths, only to be warmed once more and begin the cycle again. It is a planetary-scale lava lamp, its rhythm measured in millennia. This immediately presents the central thermal puzzle. What is the actual source of the heat driving this relentless engine? The most intuitive answer would be the distant sun, but the math simply doesn't support it. The sunlight that reaches Pluto is about 1,000 times weaker than what we enjoy on Earth. While it does provide some energy, detailed calculations show that solar heating alone is far too weak to power convection in a slab of ice several miles thick. It might affect the very top millimeter of the surface, but it cannot provide the deep-seated warmth needed to make entire cells of ice slowly boil. This forces us to look inward to Pluto's own hidden reserves of heat. The dwarf planet's rocky core is likely still warm from the energy of its formation over 4 billion years ago, supplemented by the ongoing decay of radioactive elements like potassium, uranium, and thorium. This radiogenic heat trickles outward, providing a steady, if faint, internal glow that could be just enough to get the nitrogen ice moving. But there's another, more subtle player in this thermal game: the latent heat released by the nitrogen itself. As the surface ice cools and sinks, it undergoes a phase change, transitioning and releasing a small amount of energy in the process. This released heat can then contribute to warming adjacent pockets of ice, creating a self-sustaining feedback loop within the convection cell. The system isn't just running on primordial heat from the core, it is also efficiently recycling and utilizing its own energy to keep the process going. This intricate combination of internal radiogenic warmth and self-generated phase change heat creates a delicate and perfectly balanced system, one that is powerful enough to reshape a world, yet so finely tuned that it operates on the very edge of feasibility, explaining why we don't see such spectacular convection on every other icy body in the Kuiper belt. But our exploration of Pluto's atmospheric mysteries doesn't end at its own thin, hazy skies. It extends over 20,000 miles to its largest moon, Charon, where we find a feature so dramatic it was named after the dark land of Mordor from fantasy literature. This is Mordor Macula, a vast, sprawling red stain that smothers Charon's north pole in a deep, rusty hue. Its existence is a profound puzzle in its own right, but its potential connection to Pluto makes it one of the most captivating mysteries in the entire system. How did this enormous, localized deposit of complex organics form on a world that, by all accounts, should be a dead, geologically static ball of ice and rock? The most compelling theory suggests we are not looking at two separate worlds, but one interconnected system where Pluto's atmosphere is actively leaking into space and painting its moon. Charon itself lacks any significant atmosphere. It has no blanket of gases to protect it or to drive complex chemistry on its surface. So the material that makes up this red cap cannot be homegrown. It must have been delivered from elsewhere. This is where Pluto enters the story. We know that Pluto's tenuous nitrogen and methane atmosphere is constantly escaping into space, a slow but persistent leak driven by the weak solar wind. This creates a thin, temporary neutral cloud of gas atoms orbiting Pluto. Because Charon and Pluto are tidally locked in their close dance, always showing the same face to each other, Charon's orbit consistently takes it through this ethereal cloud of material escaping from its parent world. It's as if Charon is perpetually flying through a fine, cosmic mist exhaled by Pluto. The journey of a simple methane molecule from Pluto's heart to Charon's pole is a dramatic one. Once these molecules escape Pluto's weak gravity, they are vulnerable to the Sun's powerful ultraviolet radiation. Just as it does in Pluto's upper atmosphere, this UV light shatters the methane molecules, creating highly reactive fragments. These radicals then combine with other atoms, including nitrogen, to begin forming the more complex hydrocarbons and nitriles that are the precursors to tholins. This chemical processing begins in space during the relatively short journey between the two bodies. By the time this cloud of processed gas encounters Charon, it is already primed to become the ruddy, complex gunk we see. But why does it deposit so specifically at Charon's pole? The answer lies in Charon's extreme environment and its lack of an atmospheric buffer. Without an atmosphere to distribute heat evenly, the moon's poles experience the most radical temperature swings. During its long winter, a pole is plunged into continuous darkness for decades, with temperatures plummeting to the lowest points in the entire Pluto-Charon system. This creates an incredibly efficient cold trap. When the tholin precursors from Pluto's atmospheric mist encounter these frigid polar regions, they freeze instantly onto the surface, effectively snowing out of the sky. Then, when the long polar summer finally arrives and the sun rises, the highly volatile ices like nitrogen or methane that may have co-deposited will sublimate back into space. But the more resilient, less volatile tholins are left behind, building up in a concentrated and permanent stain over millions of seasonal cycles. This process, repeated eon after eon, has resulted in the thick, dark red cap we see today. This theory of interplanetary paintball is elegant, but it raises its own set of difficult questions. Is the sheer volume of material escaping from Pluto sufficient to account for the extensive and dark deposit on Charon? The transfer of atmosphere from a planet to its moon is a phenomenon we've observed elsewhere, most famously between Jupiter and its moon Io, but the scale and specificity here are unique. Furthermore, the precise chemical pathway exactly which molecules are formed during the transit and how they ultimately combine on Charon's surface is a complex process that is difficult to model from afar. The presence of Mordor macula suggests that the Pluto-Charon system is far more dynamically connected than we ever imagined, a binary world where one body's breath becomes the other's defining feature, a permanent testament to their shared history in the cold depths of the Kuiper belt. And high above these floating hills and convecting plains, New Horizons revealed an atmospheric spectacle that left scientists utterly mesmerized. As the spacecraft looked back at Pluto, silhouetted against the sun just after its closest approach, it captured images of the dwarf planet's atmosphere transformed into a dazzling, luminous halo. This wasn't a uniform glow, but a complex, structured system of over 20 distinct and separate haze layers, stacked one upon the other like the delicate layers of a cosmic onion. These layers began at the surface and extended an astonishing 100 miles into the sky, a reach far greater than any model had predicted for such a tenuous atmosphere. The very existence of this intricate, multi-layered haze structure presented a beautiful and immediate mystery, revealing that the processes occurring in Pluto's thin air are far more complex and dynamic than we ever imagined. The composition of these haze layers provides the first clue to their origin. They are not made of dust or water vapor like clouds on Earth. They are composed of tiny, solid particles of complex hydrocarbons known as tholins. These particles are born from the interaction of sunlight with the simple gases in Pluto's atmosphere. The sun's ultraviolet radiation acts like a cosmic scalpel, slicing apart the molecules of methane and nitrogen that have sublimated from the surface ices. These fractured, highly reactive pieces then collide and stick together in the upper atmosphere, gradually growing into larger and larger clusters until they form the tiny, reddish haze particles that give Pluto's sky its beautiful blue tint and create the dramatic layers we observe. This process, known as photochemistry, is the engine that manufactures the haze, but it doesn't explain the stunningly organized, laminated structure. This is where the mystery truly deepens. On a world with such minimal atmospheric pressure, you would expect these tiny particles to be distributed evenly by whatever faint winds exist, creating a smooth, homogeneous haze. Instead, we see these sharply defined, separate layers, some of them stretching horizontally for hundreds of miles while being vertically incredibly thin. This precise organization points to the presence of a previously unknown atmospheric phenomenon actively shaping and shepherding these particles. The leading theory suggests that these layers are actually the visible fingerprints of atmospheric gravity waves. Unlike the gravitational waves of astrophysics, these are a common phenomenon on Earth, created when air is forced over a topographic feature like a mountain range. The displaced air then oscillates as it seeks to restore its balance, creating a regular, wave-like pattern in the atmosphere itself. On Pluto, the same physics are at play, but the landscape is alien. As wind flows over Pluto's massive water ice mountains and the dramatic topography of its bright and dark terrains, it is forced upward and then begins to oscillate in a steady, rhythmic pattern. These vertical waves propagate high into the atmosphere. At the crest of each wave, the air expands and cools, while at the trough it compresses and warms. The tiny tholin particles are incredibly sensitive to these subtle changes in temperature and pressure. They likely condense and become more concentrated at the specific altitudes where the waves cause the air to cool, effectively freezing them in place within these narrow bands. The haze layers, therefore, are not static features. They are a dynamic, real-time map of these invisible atmospheric waves, a visual record of the gentle, rhythmic breathing of Pluto's sky as it flows over its rugged surface. Yet, gravity waves alone may not tell the whole story. The incredible height of the haze layers suggests another, more surprising force might be at work: buoyancy. The tholin particles, as they grow larger, are eventually pulled downward by Pluto's gravity. However, the weak sunlight at that distance may be imparting a tiny but significant amount of energy onto these dark particles through radiation pressure, effectively giving them a slight push and slowing their descent. This could create a delicate balance where particles of a certain size are suspended at specific altitudes for long periods, enhancing the formation of distinct layers. Furthermore, the electrostatic forces between these particles could cause them to clump together in specific ways or align along the lines of Pluto's weak magnetic field, adding another layer of complexity to their structured arrangement. The enduring presence of these layers shows that Pluto's wispy atmosphere is not a passive shroud but an active, dynamic laboratory where chemistry and physics conspire to create beauty and order on a grand scale. Leaving the floating hills and the layered haze behind, we now descend to a region so strangely textured that scientists could only describe it by comparing it to the natural world's most intricate patterns. This is the so-called snakeskin terrain of Tartarus Dorsa, a vast landscape where Pluto's surface is etched into a breathtaking mosaic of sharp, overlapping ridges that look eerily like the scales of a giant reptile or the stretched skin of a snake. The New Horizons images revealed this texture in stunning detail, showing a network of bladed ridges aligned in consistent directions, creating a pattern of incredible complexity that is utterly unique in our solar system. Its existence is a profound geological puzzle, forcing us to confront the question of how such an intricate and organized landscape could form on a frozen world billions of miles from the Sun. The composition of these scales provides the first vital clue. Spectral analysis confirms they are made primarily of solid methane ice, the same material that forms the immense blade-like structures found elsewhere in Tartarus Dorsa. This tells us we are looking at a landscape sculpted not by internal forces pushing mountains upward, but by external forces relentlessly carving the surface away. The leading theory points to a powerful and sustained period of erosion driven by sublimation, the process where solid ice turns directly into gas without ever becoming a liquid. On Pluto, the weak sunlight provides just enough energy to cause patches of methane ice to vaporize slowly over astronomical timescales. But this isn't a uniform process, it's a selective one that acts differently depending on the angle of the Sun and the topography of the ice itself. Imagine a vast sheet of methane ice that once blanketed this entire region. As Pluto's extreme seasons slowly changed over millennia, the angle of the sunlight striking this sheet would have shifted. The sun's rays would have hit the ice at a shallower angle, warming certain slopes more than others. The areas receiving more direct sunlight would have sublimated faster, etching deep grooves and troughs into the surface. The more shielded areas, remaining colder, would have sublimated much more slowly, leaving behind the sharp, towering ridges we see today. This process, repeated cycle after cycle for millions of years, would have gradually sculpted the entire ice sheet into this spectacular ridged landscape. It's as if a cosmic artist used sunlight as a chisel, patiently carving this intricate design into the very fabric of Pluto. Yet, the incredible organization and uniformity of the pattern suggest that this wasn't a chaotic process. The ridges aren't random, they are aligned, indicating that the direction of the sunlight and the flow of Pluto's thin atmosphere played a coordinated role in their creation. The alignment is likely a permanent record of the prevailing wind patterns at the time the ridges were forming. As the methane sublimated, the resulting gas would have created a very local, thin atmosphere just above the surface. Gentle winds flowing across this landscape could have then enhanced the sublimation on the windward sides of nascent ridges, while depositing a faint frost on the leeward sides, sharpening the features and aligning them all in the same direction. This would make the snakeskin terrain a gigantic fossilized weather vane, preserving the direction of ancient winds on a world without a traditional weather system. The sheer scale of the features presents another formidable mystery. These ridges are not small, some stand hundreds of feet high. This tells us that the original deposit of methane ice must have been astonishingly thick, perhaps a mile deep or more, to allow for such dramatic sculpting. This forces the question of origin. Where did such a massive, pure reservoir of methane ice come from? Was it delivered by a bombardment of methane-rich comets in Pluto's distant past, or did it outgas from the dwarf planet's interior in a massive, singular event, creating a concentrated layer that was then shaped by the elements? The snakeskin pattern is therefore more than just a surface texture. It is the final chapter in a long and complex history, a story written in ridges of methane ice that we are only just beginning to learn how to read. This grand migration of volatiles across Pluto's surface is one of the most dynamic and visually striking processes shaping the dwarf planet, a slow-motion weather cycle operating over centuries. We see its effects everywhere, in the bright, frosty caps on mountain peaks, in the stark contrast between the white heart and the dark highlands, and in the puzzling patches of different ices scattered across the landscape. The driving force behind this movement is simple yet powerful: the search for cold. On a world with an axial tilt that creates seasons lasting for decades, certain areas become permanent cold traps, the coldest places on the planet where volatiles go to stay. As temperatures shift with Pluto's long orbit, these ices don't just sit still. They take a journey, sublimating from warmer areas, traveling as gas in the thin atmosphere, and then refreezing onto the coldest available surfaces. It's a global game of musical chairs dictated by temperature, with the music provided by the distant sun. The most dramatic example of a cold trap is the immense basin of Sputnik Planitia itself. This region sits several kilometers below the surrounding terrain, and as we know, cold air sinks. This makes it the single coldest place on Pluto, a massive depression where both literal and metaphorical cold collects. This is why it is able to hold onto its vast sheet of nitrogen ice while other, higher areas cannot. The nitrogen molecules sublimating from elsewhere on the planet eventually drift through the atmosphere until they encounter this profound chill, at which point they condense and freeze, adding another microscopic layer to the glacier. It acts as Pluto's primary cold trap, a gravitational anchor for volatile ices that has been collecting this material for perhaps billions of years. But the process is far more selective and complex than a simple blanket accumulation. This is where the mystery of volatile transport truly deepens. We see that methane ice behaves very differently from nitrogen ice, and carbon monoxide behaves differently still. Each volatile has its own unique freezing point. Nitrogen is the most volatile, meaning it requires the very coldest temperatures to stay frozen. Methane is a bit less volatile, and water ice is essentially bedrock, completely non-volatile at Pluto's temperatures. This creates a sophisticated fractional distillation system across Pluto's topography. The high-altitude mountain peaks, while cold, are just that tiny bit warmer than the deepest basin floors. They are just warm enough that nitrogen ice finds it energetically unfavorable to freeze there, but they are perfectly cold enough to be a stable home for methane frost. This is why we see brilliant white methane caps on the mountaintops, but not on the lower plains. The mountains are the perfect Goldilocks zone for methane, while the deep basins are the exclusive domain of nitrogen. The sheer scale of this transport is difficult to comprehend. We are talking about the movement of ice deposits that could be hundreds of meters thick across distances of thousands of miles, all driven by temperature differences of perhaps only tens of degrees. The timescales involved are equally staggering. A single seasonal cycle on Pluto lasts for over a century, meaning a full circuit of a volatile molecule from ice to gas and back to ice in a new location could take millennia. This forces us to question whether our snapshot from New Horizons, a single moment in this immense cycle, is showing us a balanced state or a transient one. Is the distribution of ices we see today the permanent, final result of this process? Or are we merely catching Pluto in the middle of a slow-motion resurfacing event that will look completely different 100,000 years from now? Perhaps the greatest unanswered question is how this cycle has shaped Pluto's geology over billions of years. The constant sublimation and deposition of these massive ice sheets represents a powerful form of erosion and construction. As ices sublime from one area, could they be leaving behind the heavier, darker tholins to form a concentrated lag deposit, explaining the dark equatorial belts? As they freeze in another, are they building up layers that eventually become thick enough to convect, creating features like the polygonal cells of Sputnik Planitia? The volatile cycle isn't just painting the surface. It may be one of the primary architects of Pluto's entire geological identity, a slow but relentless force that has carved, built, and colored this distant world in ways we are only beginning to decipher. Nestled within the sprawling darkness of Cthulhu Macula lies an area so profoundly dark it was named after a lord of the underworld in Mandean mythology, Crun Macula. This region represents one of the most light-absorbing surfaces ever observed on a planetary body, a vast, sprawling blemish where the already dark Tholen coating seems to have reached its absolute extreme. While we understand that tholins are the complex, reddish-brown organic polymers that snow down from Pluto's atmosphere, the existence of a region as intensely dark as Crun Macula forces us to ask a more specific and challenging question: why here? What unique combination of atmospheric and geological conditions on Pluto has conspired to concentrate this cosmic soot into such an exceptionally dark and defined patch, creating a permanent shadow on a world already rich in contrast? The composition of the material itself is the first layer of the mystery. Tholins are not a single compound but a vast family of complex macromolecules formed when simple gases like methane and nitrogen are zapped by ultraviolet radiation or charged particles. The specific recipe for Pluto's particular blend of tholins is unknown, but laboratory experiments on Earth that simulate its atmospheric conditions produce a sticky, reddish-brown tar-like substance often described as a prebiotic goo. It's rich in carbon, hydrogen, and nitrogen, the very building blocks of life, though not life itself. The profound darkness of Crun Macula suggests that this material has not only accumulated there in immense thickness, but has also perhaps undergone further processing. The constant, feeble bombardment of cosmic rays and solar UV on the surface could be slowly carbonizing this organic sludge, baking it into an even darker, more charcoal-like substance over millions of years. It's possible that Crun Macula isn't just a thick layer of tholins. It might be the most well-done, thoroughly cooked patch of organic material on the entire dwarf planet. Yet, composition alone doesn't explain its location and defined nature. The accumulation of such a dark deposit points directly to a geological surface that has been utterly static for an immense period. Crun Macula resides within Pluto's oldest terrain, a landscape that has witnessed no significant resurfacing events for billions of years. Unlike the dynamic, churning engine of Sputnik Planitia that constantly buries any surface deposits, the geology here is fossilized. This has allowed the Tholin snow to fall, settle, and build up into a layer of incredible depth without any disturbance. It acts as the ultimate cosmic dust trap, a geological dead zone where the slow, steady rain of hydrocarbons from the sky has been collected and preserved since the solar system's youth. The role of atmospheric circulation provides the final, critical piece of the puzzle. Pluto's thin atmosphere isn't uniform. It likely has patterns and currents, however faint. The extreme temperature differences between the bright, reflective ice plains and the dark, heat-absorbing regions can set up gentle but persistent wind patterns. Scientists theorize that Crun Macula may sit at the end of a prevailing atmospheric conveyor belt. The processes that create Tholin haze occur high in the atmosphere, and these tiny particles must eventually fall. It's possible that global wind patterns or localized circulation cells consistently guide this haze toward certain latitudes, causing it to precipitate out more heavily over specific regions. Crun Macula could be the planetary equivalent of a rain shadow or a deposition zone, where the atmospheric dynamics conspire to dump the majority of their complex organic cargo, creating a concentrated stain that has grown darker with every passing eon. This makes the region more than just a passive stain. It is an active chemical repository, a library of Pluto's atmospheric history written in layers of complex carbon, waiting silently for us to learn how to read its pages. And now we turn to what may be the most visually spectacular evidence of Pluto's surprisingly violent past: vast, sprawling plains that look for all the world like frozen rivers of lava. But this is not the scorching basalt we find on Earth or the Moon. If the interpretations are correct, this is cryolava, a frigid, slushy mixture of water ice, perhaps mixed with ammonia or other antifreezes, that oozed across Pluto's surface before freezing solid. The most prominent of these suspected flows is found on the flanks of Right Mons, the massive cryovolcanic candidate, where broad, lobate sheets of material seem to have spilled out from the summit caldera and flooded the surrounding terrain. These features present a breathtaking geological puzzle, forcing us to confront two monumental questions. Could water ice truly have flowed like lava on this frozen world? And if so, what incredible source of heat could have possibly powered such an event? The case for these being cryolava flows rests on their striking morphological similarities to volcanic flows we see throughout the solar system. In high-resolution New Horizons images, these plains exhibit a smooth, relatively uncratered surface that drapes over and fills in older topography, much like a liquid wood. They often show distinct lobate margins, rounded, flow front edges where the advancing material finally came to a stop. In some areas, the texture appears ropey or folded, reminiscent of the Pahoho lava flows from Hawaiian volcanoes, suggesting a viscous fluid that was still moving as its surface skin began to congeal. The composition of these flows, as determined by spectral data, is just as telling. They are rich in water ice, but not in its familiar brittle form. The ice here shows a spectral signature consistent with a more amorphous or crystalline structure, the kind that might be expected if it had been flash melted and then rapidly frozen, preserving the altered state. Yet the very idea of water ice lava creates a profound thermal paradox. For water ice to behave as a fluid on Pluto's surface, it must be heated to temperatures near its melting point. But with surface temperatures hovering around -380 degrees Fahrenheit, the environment is hundreds of degrees too cold for pure water ice to ever flow. This is where the concept of antifreeze becomes critical. Scientists posit that the cryomagma couldn't have been pure water. It almost certainly contained a significant amount of ammonia, a known antifreeze that forms a hydrate with water and can lower its freezing point by nearly 200 degrees. Salts, such as those found in the subsurface oceans of moons like Europa, could have further depressed the freezing point, creating a cold, briny slurry viscous enough to ooze across the landscape before finally solidifying into the features we see today. This explanation, however, only shifts the mystery deeper underground. The real enigma is not the flow itself, but the engine that could have melted the ice in the first place. To produce even this ammonia-rich slurry requires a formidable and concentrated heat source. On active moons like Enceladus or Io, such heat is provided by intense tidal friction from their gravitational interactions with a giant planet. But Pluto lacks a massive planetary neighbor to squeeze and stretch its interior. The most likely candidate is the long-lived decay of radioactive elements like potassium, uranium, and thorium within Pluto's rocky core. The problem is that for a body Pluto's size, models suggest this radiogenic heat should have largely dissipated billions of years ago, or at best provided a gentle background warmth insufficient for large-scale melting. This has led to more exotic and fascinating theories. One possibility is that the heat was generated by a massive impact event. The tremendous energy released when a large Kuiper belt object slammed into Pluto could have created localized pockets of melt, flash heating the ice and allowing it to erupt onto the surface in a catastrophic event. Alternatively, the heat could be a delayed effect of Pluto's own formation. If the dwarf planet accreted from material that included a higher-than-expected proportion of radioactive isotopes, it could have started with a much hotter inventory, and that heat might still be working its way out through the crust in sporadic, violent episodes. The most intriguing possibility is that we are seeing the result of the crystallization of a subsurface ocean. As a hidden ocean of water slowly freezes from the bottom up, the process of crystallization releases latent heat. This released energy could be focused upward, occasionally becoming intense enough to melt the base of the ice shell and trigger a cryovolcanic eruption, creating a temporary and spectacular release of cryolava that belies the world's frozen exterior. But perhaps one of the most elegant and unexpected theories for how Pluto holds onto its atmosphere involves its largest moon, Charon. The two worlds are tidally locked in a tight gravitational dance, and some scientists propose that Charon might actually be acting as a shield. As Pluto plows through the solar wind, its moon could be positioned in such a way that it periodically blocks a portion of the incoming particle stream, creating a temporary wake of relative calm in its lee. This wouldn't stop the erosion entirely, but it could provide a periodic respite, slowing down the process in a way that isn't available to a solitary, unprotected world. It's a fascinating idea that Pluto's companion, rather than being a passive bystander, might actively help preserve the very atmosphere that gives the dwarf planet its complex and dynamic character. To truly grasp the bizarre and dramatic nature of Pluto's seasons, we must first reorient our entire perspective on what a year really means. Imagine a world where the concept of north and south is almost meaningless, a planet that doesn't so much tilt on its axis as it practically rolls around the sun on its side. With an axial tilt of 122 degrees, Pluto is more severely tilted than even Uranus. This means its poles are not merely pointed toward the sun during their respective summers. For all practical purposes, one entire hemisphere is continuously bathed in sunlight while the other is plunged into a deep, endless night for decades at a time. A single day on Pluto lasts about 6.5 Earth days, but a single season lasts for a staggering 60 to 100 Earth years. This isn't just a climate. It's a slow-motion celestial drama where the stage itself undergoes a radical transformation over a timescale longer than a human lifetime. The immediate and most visible consequence of this radical tilt is the utterly wild redistribution of surface ices across the dwarf planet. During a poles-long summer, the constant sunlight provides just enough energy to cause the volatile ices coating that hemisphere, primarily nitrogen, but also methane and carbon monoxide, to sublimate directly into the atmosphere. This doesn't happen gently or evenly. It's a planetary-scale evaporation event. The atmosphere thickens with these gases, and prevailing winds, however faint, carry them across the globe. They journey toward the opposite hemisphere, which is in the grip of its decades-long winter. There, in the profound and unending cold, these gases encounter a massive cold trap. They refreeze onto the surface, snowing down and building up a fresh, bright cap of ice that will remain for decades. Over the course of Pluto's 248-year orbit, this process effectively seesaws back and forth, with entire ice caps potentially vanishing from one pole and reappearing at the other. This incredible seasonal pump is the leading theory behind the massive ice sheets we see, particularly the location of Sputnik Planitia. Some scientists speculate that this heart-shaped feature might not be a permanent fixture. It could be the current resting place for this seasonal seesaw of volatiles, the primary cold trap for this particular epoch in Pluto's long history. Its location near the equator is itself a puzzle, as the poles are typically the coldest places on a planet. This suggests that other factors, like the basin's low elevation and its composition, make it an exceptionally efficient cold trap, overriding the usual polar preference and locking a significant portion of the planet's volatile inventory in one place for now. The unanswered question is whether this is a permanent state or a temporary one. Will Sputnik Planitia eventually lose its ice as the seasons continue to shift over millennia, with a new ice cap forming somewhere else entirely? The impact on Pluto's atmosphere is equally extreme and far less understood. Our models predicted that as Pluto moved away from its closest approach to the Sun, its atmosphere should have begun a steady and rapid collapse, freezing back onto the surface. New Horizons proved this simple model wrong. the atmospheric pressure was far higher than expected, suggesting the system has a tremendous amount of thermal inertia. The ices on and beneath the surface appear to be acting like a giant battery, storing heat from the long summer and releasing it slowly throughout the subsequent fall and winter, continuing to feed the atmosphere long after the external energy source has faded. The sheer thickness of the ice deposits means this process could have a delay of years or even decades, making it incredibly difficult to model and predict how the atmosphere will behave at any given point in the orbital cycle. We essentially have a single snapshot of Pluto's climate from New Horizons, and we're trying to extrapolate a centuries-long weather forecast from it. Perhaps the deepest mystery locked within Pluto's extreme seasons is their potential role in driving the planet's long-term geological cycles. The repeated, massive loading and unloading of billions of tons of ice from one hemisphere to another could have profound effects on the world's very structure. This process, known as true polar wander, where the redistribution of surface mass causes the entire planet to slowly reorient itself to maintain spin balance, might be a recurring event on Pluto. The seasonal seesaw could be the engine that periodically reshapes the planet's face over millions of years. Furthermore, the drastic temperature swings between the seasons could be the key to forming features like the bladed methane terrain. The prolonged periods of sunlight during a hemisphere's summer might provide the sustained energy needed for the intricate sublimation erosion that carves these jagged ridges, while the long winters allow them to freeze and preserve their sharp forms. Pluto's extreme tilt and marathon seasons are not just a climatic curiosity. They are likely the fundamental driver behind its most iconic and enigmatic landscapes, a slow, powerful rhythm that has dictated the evolution of this distant world for billions of years. But the intrigue of Pluto's celestial family extends far beyond its binary partner Charon, to the chaotic dance of its four smaller moons, Styx, Nix, Kerberos, and Hydra. The leading theory for their origin is a dramatic and violent one, a cosmic event so colossal it echoes the very formation of our own moon. Billions of years ago, in the chaotic early solar system, a primordial Pluto is believed to have been struck a glancing blow by another massive object, perhaps another large Kuiper belt body. This catastrophic impact would have vaporized a tremendous amount of material from both bodies, hurling a vast cloud of debris into orbit around a reeling, wounded Pluto. Over time, the laws of physics took over as gravity began to corral this scattered debris, accreting it into the moons we see today. This elegant Genesis story, however, immediately unravels when we look closely at the moons themselves, whose bizarre properties present a series of deep and unresolved puzzles. The first glaring mystery is their utterly chaotic and unpredictable rotation. Unlike our moon, which is tidally locked to Earth and shows us only one face, Pluto's smaller moons are tumbling through their orbits in a state of pure pandemonium. They do not spin at a constant rate or around a stable axis. Their rotation rates are unpredictable, and their poles might as well be flipped entirely from one year to the next. This behavior is so extreme that if you were standing on the surface of Nix or Hydra, you would not experience a normal day-night cycle. The sun would rise and set in random parts of the sky, and the length of a day would change constantly. This chaos is a direct challenge to the formation model. If the moons coalesced gently from a disk of debris, their rotations should have been stabilized by gravitational interactions long ago. Their continued tumbling suggests they are being violently perturbed by the complex gravitational field of the Pluto-Charon binary, a gravitational dance so intense it prevents them from ever settling down. Adding to the confusion are their highly irregular, non-spherical shapes. These are not neat, round worlds like our moon. They are best described as cosmic potatoes or ragged lumps. Hubble and New Horizons imagery revealed them to be elongated and misshapen, looking more like rubble piles hastily assembled than properly formed planetary bodies. Their shapes directly reflect their weak gravity, which is too feeble to pull them into a sphere, but this also raises a question about their internal structure. Are they solid bodies, or are they fragile aggregates of ice and rock, barely held together? Their irregular forms make their orbits even more complex to calculate, as their uneven mass distribution interacts with gravity in subtle, constantly shifting ways, contributing to their chaotic spin states and making their long-term orbital futures incredibly difficult to predict. The specific conditions of the ancient impact itself are another realm of pure speculation. For the impact theory to produce the system we see today, the collision had to be a very specific kind of hit, powerful enough to eject sufficient material to form all 5 moons, but not so devastating that it completely obliterated Pluto. The angle, speed, and size of the impactor are all variables that dramatically change the outcome. Computer models struggle to find a single impact scenario that perfectly accounts for the current orbits, masses, and bizarre properties of all the moons. It's possible we are seeing the result of a more complex series of events, perhaps multiple smaller impacts that added material to the system over time, or a single impact that created a disk of debris which then fragmented and collided again before finally forming the moon. Each moon, with its unique orbit and composition, could be telling a slightly different chapter of this violent origin story. Perhaps the most captivating mystery of all lies in the surfaces of these moons, particularly Nix and Hydra. New Horizons data indicated that at least some of them are surprisingly bright and reflective, with surfaces that appear to be coated in relatively clean water ice. This is puzzling because a cloud of impact debris should have been a messy mixture of rock and ice from the interiors of both colliding bodies. The processes that could have somehow sorted this material, leaving the moons with bright, icy surfaces while the darker, rocky material was lost or settled elsewhere, remain completely unknown. Their bright surfaces also make them incredibly vulnerable to the relentless rain of cosmic radiation and micrometeorites in the Kuiper belt, which should darken them over time. Their persistent brightness suggests that some form of geological activity, however minimal, might be refreshing their surfaces, a shocking possibility for such tiny, distant worlds. The origin of Pluto's moons is not a settled chapter in a textbook. It is a wide-open question, a reminder that even the most widely accepted theories in planetary science can be upended by the strange and wonderful realities of the cosmos. And now we arrive at a mystery that lies not in grand geological features, but in the very light they reflect a puzzle written in the intricate language of spectra. When New Horizons' Ralph instrument analyzed Pluto, it didn't just take pictures. It dissected the sunlight bouncing off the surface, breaking it down into its constituent colors to create a unique chemical fingerprint for every patch of ground. This data revealed a world of stunning spectral diversity, where the signatures of water, nitrogen, methane, and carbon monoxide ices appear in wildly different combinations and purities across the landscape. The very fact that these ices are so unevenly distributed presents a profound challenge, forcing us to move beyond simple textbook explanations and confront the complex, real-world chemistry of a distant, active world. The fundamental puzzle begins with the concept of volatility. In the incredibly cold environment of the Kuiper belt, a substance's volatility determines its behavior, how easily it transforms from a solid to a gas. The textbook model, based on volatility alone, would predict a neat, layered separation of these ices. Nitrogen is the most volatile, so it should dominate the coldest traps like the deep basin of Sputnik Planitia. Methane, being less volatile, should coat the higher, slightly warmer terrain. Carbon monoxide, with a volatility between the two, should be found in an intermediate zone. And water ice, almost rock-like in its stability at these temperatures, should form the immovable bedrock everywhere. Yet, the spectral maps from Ralph tell a far more complicated and fascinating story. While Sputnik Planitia is indeed a vast reservoir of nitrogen, it also contains significant patchy deposits of carbon monoxide and methane. Meanwhile, the rugged water ice mountains are frequently capped with brilliant methane frost, and dark, tholin-stained regions show almost none of the expected volatile ices at all. This isn't a neat, stratified layer cake. It's a messy, marbled cake where the ingredients have been swirled together by a chaotic cosmic baker. This disconnect points to processes that are actively working against simple volatility sorting. The churning convection within Sputnik Planitia is a prime example. This constant, slow-motion overturning doesn't just refresh the surface. It acts like a gigantic blender, churning together the nitrogen, methane, and carbon monoxide ices that were deposited there. This mechanical mixing creates a heterogeneous cocktail of ices that would otherwise separate into pure layers over time. It's a dynamic process that constantly fights against the tendency for these materials to sort themselves out by their weight and volatility, ensuring the surface composition remains a complex patchwork. Beyond simple mixing, the spectra also hint at more intimate chemical relationships between these ices, particularly the puzzling partnership between nitrogen and carbon monoxide. Their spectral signatures in Sputnik Planitia are often found together in a consistent ratio, suggesting they might be forming a solid solution or clathrate, a cage-like structure where one type of molecule is trapped within the crystal lattice of another. This kind of molecular partnership can dramatically alter the physical behavior of both ices, changing their individual volatility, strength, and spectral properties. A nitrogen-carbon monoxide clathrate would be a completely new type of material for planetary scientists to study, one that could behave in ways we don't fully understand, potentially explaining why these two ices stubbornly remain together in places where simple models say they should have long since parted ways. The role of water ice as a stable substrate adds another critical layer to the mystery. The spectral data clearly shows that methane frost has a strong preference for coating water ice mountains, while it avoids the nitrogen-dominated plain. This is a powerful example of surface chemistry trumping atmospheric chemistry. A methane molecule landing on the dynamic, convecting surface of Sputnik Planitia doesn't have a stable foundation. It's quickly buried, destroyed by radiation, or sublimates away. But that same molecule landing on the hard, cold, and unchanging water ice bedrock of a mountain peak finds a permanent home. The water ice provides a stable, welcoming surface for the methane to adhere to and build up a bright, long-lasting frost. This means the distribution of one ice is fundamentally controlled by the presence and stability of another, creating a geological dependency that simple volatility models could never predict. Finally, we must consider the relentless processing by solar radiation, which doesn't just create tholins in the atmosphere, but also alters the ices right on the surface. The same ultraviolet light that paints Pluto's poles red is constantly bombarding the exposed methane frost on the mountaintops. Over time, this radiation can break apart methane molecules or change the crystalline structure of the ice, subtly altering its spectral signature and potentially making it less volatile. This creates a feedback loop where the distribution of ices we see today is not just a snapshot of current conditions, but a palimpsest, a record written over by eons of chemical and radiological processing. The spectral uniqueness of Pluto's ices is therefore more than just a map of what's there. It is a complex historical document recording the interplay of atmospheric escape, geological activity, chemical bonding, and solar radiation across billions of years. It shows us that Pluto is not a passive ball of ice slowly relaxing into equilibrium, but a dynamic, chemically complex world that is actively managing its volatile inventory in sophisticated and surprising ways. And as we scrutinize the highest resolution images sent back by New Horizons, we encounter a set of markings so geometrically perfect they seem almost artificial. Dotted across certain regions of Pluto's complex landscape are enigmatic features informally dubbed the X marks. These are not the bladed ridges of Tartarus Dorsa or the polygonal cells of Sputnik Planitia. These are stark, intersecting linear fractures that form a near-perfect cross, their sharp angles standing out with unnatural clarity against the chaotic backdrop of ancient cratered terrain. Their precise, manufactured appearance is so striking that it immediately sparks the imagination, but for planetary geologists, they present a superb and tangible puzzle rooted in the fundamental forces shaping this frozen world. The most logical explanation points to Pluto's internal stresses and the resulting tectonic activity. As the dwarf planet cooled over billions of years, its outer water ice shell would have contracted. Different layers of this icy crust, each with a slightly different composition and temperature, would have contracted at different rates, creating immense shear forces between them. This stress must be released, and it often does so by fracturing the brittle surface ice. The X features could represent the intersection point of two such deep-seated fault systems. When the stress field is oriented in just the right way, it can cause fractures to propagate in two predominant directions that are perpendicular to each other, creating these perfect cross-shaped intersections. It would be the geological equivalent of the stress patterns you see in drying mud or in the thawing ice on a parking lot, but operating on a planetary scale and over millions of years. However, the tectonic theory immediately runs into a complicating factor: the apparent freshness of some of these features. In some images, the X marks appear crisp and sharp, with little evidence of the degradation or infilling that would be expected from features that are billions of years old. This suggests they might be geologically young, which in turn implies that the forces creating them are still active today. This brings us back to the profound mystery of Pluto's internal heat source. What could possibly be generating enough ongoing thermal contraction or expansion to fracture the ice so recently? Is it the residual cooling from formation, the gentle heat from radioactive decay, or could it be linked to the slow freezing and expansion of a subsurface ocean, which would exert new pressures on the overlying shell? The X marks might be the surface expression of deep, ongoing change within Pluto, a sign that its interior is still dynamically settling and shifting. A competing and equally compelling theory suggests these features are not being pushed up from below, but are instead being carved down from above by the relentless process of sublimation. This would make them cousins to the bladed terrain, but on a different scale and with a different orientation. The idea is that the initial fracture could be a simple, pre-existing crack in the ice, perhaps from a small impact or an old tectonic line. Once this weakness exists, it becomes a preferred site for sublimation. The sun's feeble energy would be channeled more efficiently into the crack, causing the ice at those specific lines to vaporize faster than the surrounding terrain. Over eons, this would etch the fracture pattern deeper and wider, sharpening its edges and creating the clean, linear troughs that form the cross. The specific orientation of the arms could then be a direct record of the angle of the sunlight over countless seasons, or perhaps of the direction of Pluto's prevailing winds, which would help carry away the sublimated gases and enhance the erosion along those specific paths. The true origin of the X features likely lies in a combination of these processes, a partnership between internal dynamics and external erosion. A deep tectonic fault might provide the initial weakness, and then sublimation acts as a master sculptor, refining that raw fracture into the geometrically perfect form we see today. Their persistence is a testament to the stability of Pluto's surface. Once formed, these features are essentially frozen in time, with no liquid water or weather to erode them away. They remain as permanent inscriptions on the landscape, a cryptic signature left by the interplay of heat, cold, stress, and sunlight on a small world at the edge of our solar system. They are a reminder that even the simplest of shapes can hold the most complex of histories, waiting for us to decipher their code. This brings us to the final, and perhaps most poignant, mystery surrounding this distant world, the ultimate fate of the delicate atmospheric veil that gives Pluto its complex character. As the dwarf planet continues its long journey away from the Sun, moving toward the most distant and frigid part of its 248-year orbit, a critical question hangs in the balance. Will its thin blanket of gases completely collapse, freezing out in a permanent winter that leaves the surface silent and exposed? Or will this tenuous atmosphere surprise us once again, demonstrating a resilience that defies our simplest models? The answer holds the key to understanding the complete seasonal cycle of this complex world and could redefine what we know about climatic evolution on small planetary bodies throughout the cosmos. The conventional textbook model of Pluto's atmosphere, based on decades of observation and theory, paints a picture of a dramatic seasonal collapse. The logic is straightforward and seems inescapable. As Pluto's distance from the Sun increases, the amount of solar energy reaching its surface dwindles significantly. This dwindling energy means less heat is available to sublimate the volatile ices, primarily nitrogen, methane, and carbon monoxide, that make up its atmosphere. The gases currently in the atmosphere should gradually lose their thermal energy, slow down, and condense back onto the surface as fresh frost. The atmospheric pressure, already barely a whisper, should plummet towards zero. According to this view, by the time Pluto reaches its aphelion, its farthest point from the Sun sometime around the year 2113, its sky should be utterly black and clear, its atmosphere effectively gone, locked in a deep freeze on the surface for a 60-year winter. However, the flyby of New Horizons in 2015 fundamentally challenged this simple narrative. The spacecraft arrived at Pluto just 9 years after its closest approach to the Sun, a point in its orbit when the atmosphere should have already been in a period of rapid, measurable collapse. Yet the measurements told a completely different story. The atmosphere was not collapsing anywhere near as fast as the models had predicted. Its pressure, while incredibly thin, was far more robust than anyone had anticipated. This single data point was a revolution in our understanding. It proved that Pluto's atmosphere possesses a significant amount of thermal inertia. It doesn't just respond instantly to the Sun's changing warmth like a simple ice cube melting and refreezing. Instead, it behaves more like a massive thermal battery, with the thick layers of surface and subsurface ice storing heat from its long summer and releasing it slowly over decades, providing a lingering energy source that continues to power sublimation and sustain the atmosphere long after the external sunshine has faded. This introduces a fascinating and unresolved debate among planetary scientists. One camp argues that a complete collapse is still inevitable, just delayed. They suggest that New Horizons simply caught Pluto at a point where this thermal inertia was at its peak, and that the collapse, while slower than thought, will still proceed inexorably as the world plunges into deeper cold. The other camp proposes a more nuanced outcome, a partial collapse. In this scenario, the atmosphere will never fully disappear. The most volatile ice, nitrogen, might largely freeze out onto the surface, but the less volatile methane could remain in the atmosphere, creating an even thinner but permanent methane-based sky. This would fundamentally change the atmospheric chemistry and the subsequent seasonal cycle when Pluto eventually swings back toward the Sun. The long-term consequences of either outcome are profound. If the atmosphere does completely collapse and freeze, the entire surface of Pluto would be transformed. The complex processes that depend on that atmosphere would grind to a halt. The wind patterns that sculpt the dunes would cease. The production of tholins in the upper atmosphere would stop, ending the slow, continuous rain of red organic material that paints the poles and the dark equatorial regions. The surface would become a static, frozen museum, preserving its current geology under a thickening layer of new frost for decades, untouched by atmospheric weathering until the Sun's return initiates a new thaw. Conversely, if a vestigial atmosphere persists, it would maintain a dynamic, however minimal, link between the surface and the space environment. This would allow some degree of volatile transport to continue even at aphelion. Methane molecules might still hop across the surface, and the faint whispers of wind could continue their slow work. This would mean that Pluto is never truly geologically dead, even at the coldest point in its orbit. The behavior of this remnant atmosphere would provide invaluable clues about the internal heat flow and the stability of the suspected subsurface ocean, as that internal warmth could be the critical factor preventing a total atmospheric freeze. Ultimately, resolving this mystery requires something we currently lack: patience. A full understanding of Pluto's climate can only come from observing it through an entire orbital cycle, an endeavor that takes 2.5 centuries. We have a single, exquisite data point from New Horizons, a detailed portrait of the dwarf planet in its late summer. To truly know its fate, we must wait for future generations to send another probe to visit Pluto when it is at its most distant and cold, to see if its sky has indeed vanished or if it still clings to a faint, ghostly breath, a testament to the unexpected and enduring dynamism of worlds in the frozen reaches of our solar system. From the moment New Horizons beamed back its first unprecedented images, Pluto transformed from a distant, blurry speck into a world teeming with breathtaking complexity and profound, unresolved questions. We've journeyed together through 25 of its most captivating mysteries, from the dynamic, beating heart of Sputnik Planitia and its convecting nitrogen ice to the enigmatic bladed terrain that stands like a forest of frozen knives. We've explored the possibility of a hidden subsurface ocean, the bizarre floating hills of water ice, and the chaotic dance of its small moons. We've gazed upon cryovolcanoes that may erupt slushy ice, walked across plains of dunes sculpted by winds in a near vacuum, and looked up at a hazy, layered atmosphere that defies all predictions of collapse. Each discovery peeled back a layer, only to reveal yet another puzzle beneath, proving that Pluto is not a static relic but a vibrant, active world that has stubbornly refused to conform to any of our expectations. This small world on the edge of our solar system has taught us a monumental lesson about the nature of exploration. The universe reserves its greatest surprises for those who dare to take a closer look. Pluto, once dismissed as a simple ball of ice, has revealed itself as a geological wonderland, a chemical factory, and a climatic marvel, all wrapped in a package of profound beauty. Its mysteries are a powerful reminder that wonder is not confined to the warm, well-lit regions of the solar system, but thrives in the cold, dark silence of the Kuiper belt, waiting for our curiosity to unlock its secrets. The story of Pluto is far from over. It is an invitation, a challenge to the next generation of explorers to continue the work that New Horizons began. Now we want to hear from you. Which of these 25 mysteries captured your imagination the most? Does the thought of a hidden ocean beneath the ice fire your curiosity? Or are you captivated by the eerie, snakeskin texture of its frozen plains? Perhaps the chaotic tumble of its small moons or the defiant persistence of its atmosphere left you in awe. Share your thoughts in the comments below. Let's keep this conversation about the wonders of our solar system going. And if this journey to the edge of discovery sparked your sense of wonder, be sure to like this video and subscribe for more deep dives into the universe's greatest puzzles. Never stop looking up and never stop wondering what's out there, waiting in the darkness to be found.